related to hydraulics. And okay, so the projector is not on, so participants here in the lecture room are suffering a bit to see my presentation. So it's back on. Okay, so now, so the last component, and then what follows is that I'm going to explain you an example that kind of summarize everything related to hydraulic modeling. And in that summary, we're going to make the equations, or we're going to build the equations that are needed in order to compute the forces produced by a hydraulic cylinder. And the cylinder will be connected to simple hydraulic circuit. But prior to that, let's take a look. The final thing, which is a variable volume pump. And again, the idea of the variable volume pump is such that flow rate it is adjusted. So it's not necessarily producing maximum flow rate all the time, or not producing the maximum pressure or power to system, but it is adjusting that based on its need. So simply how it goes in using the drawing symbols. So if I have here a pump, the pump is producing the flow rate, the control volume, that is this one here. Control volume may be connected to some other location. Now, what is that we're doing in a fixed volume pump is that we can producing this flow rate regardless of the situation. Now, in a variable volume pump, we cannot take the measure from the pressure right after the pump, or it could be measured from other location too. Are we measuring how much pressure is actually here? And now, depending on the pressure, we can either produce more flow rate or produce less flow rate. In a sign, a drawing symbol, it means that there is adjustability. There is an ability to adjust how much flow is produced. Now, typically, if there is a fixed volume pump, then that is connected to pressure relief pump, which is, the kind of the drawing symbol like that, and that is then connected to tank. So, in case of fixed volume pump, this is like the most stupid system ever, because, we producing energy to system, and then it goes to pressure relief valve, and then back to the tank. Why it is still used? Because, when we are very so concerned about energy usage, why this is still used in certain applications? Well, the fixed volume pumps are still used because they have very good reliability. So in cases that they are sensitive for reliability, it is still a good choice, even though that is kind of losing an enormous amount of energy because, this, sorry about that, the picture is becoming a little bit mess, but there is a motor that is producing energy to system, and then it goes to pressure relief valve and then back to tank. So nothing really happens when there is no need for energy. When it's needed, then it's ready for your usage. Now this variable volume pump can actually control the amount of flow that is produced to system, and that is described mathematically, again using first order differential equation, and the differential equation goes like shown here. Now this needs a little bit of explanation. Here first of all I have here Q dot. In order to know how much flow exactly is produced, you have to again integrate this in order to be able to produce the flow rate. That's the one that goes then to this differential equation that either increase the pressure or decrease the pressure depending how much flow is coming in and how much flow is leaving out. Okay, then I have here a reference pressure, the pressure that I'm desiring, hoping to have. Again, I'm sorry that the picture is a little bit unclear. I want to change the color. Okay, then no, I'm not going to change the color. So then, how much pressure you would like to have in this particular part. So that's called reference pressure. And then you're comparing that to measurements that you're obtaining from that particular location. And if the measurement is less than the set pressure, then you're producing more flow rate to your system. If it is equal than more, you don't produce the flow rate. That's how it goes. And then I have here the flow rate in any given time that is in this equation. And this is then time concept, like how fast you can react the changes that you have in your power need that you can get from the manufacturer's catalog, and that's how it goes. More advanced, even more, the thing that is used in the mobile applications particularly, it is a load sensing control. This shortly means that you're looking the different location in your hydraulic circuit, and you're looking how much pressure is in different location of your hydraulic circuit, and based on that, you make your decision to produce more flow rate or not to produce more flow rate. To understand that, this is, by the way, very critical to understand because it's so frequently used, particularly in the mobile applications. I would like you to take a look at the video. And now let's see if how is this video is able to play, because I'm not sure what's the deal with the... Okay, let's see.
Pumps, sometimes referred to as flow compensating. Our pump still has that very heavy spring, that major adjustment called the pressure compensator or the pressure cutoff for when we hit that really high top end pressure to make sure our system is protected. But it also has a weaker spring called the load sensing adjustment or the flow compensator. And that flow compensator is receiving information, feedback if you will, coming directly from the load, our cylinder, which right now is working at 300 psi. That's the pressure it takes to lift the cylinder and rod. And that 300 psi is being fed back to the controller and giving that spring a boost. I can tell that the spring is actually set to 300 psi. How did I figure that out? I figured that out because our pump outlet pressure is set at 600. So it's taking 300 from the load and adding it to the 300 spring setting, and those two pressures add together, those two forces add together to give us our regulated pump outlet pressure of 600 psi. This is different from a pressure compensated pump, which might be set at, say, 2000 psi at all times, and therefore using a lot more input energy. So in this particular case, we've got a pump that sets its outlet pressure just slightly higher than what's needed by the load. We've got to have some kind of a flow controlling device in there. This is our needle valve that's being used to set our desired cylinder stroke speed. But let's have a look at what happens when I add a brick to the brick stacker. Our load pressure has gone up to 600. But what happened to our pump outlet pressure? Somehow it automatically adjusted from 600 up to 900. What we're finding out is that we're always maintaining a 300 psi pressure differential, sometimes referred to as a 300 psi margin pressure when we're referring to load sense systems. Let's add one more brick, and this time watch the delta P gauge. The delta P gauge fluctuates for a brief fraction of a second, but quickly we find it returns to 300 psi, and we never really noticed any change in speed at the cylinder. The cylinder just kept moving nice and steady, and our pump found out that it needed to increase the outlet pressure setting automatically. So what we found out is we can have a pump that is set at a pressure that's just a little higher than what's needed at the load, instead of being always at the pressure cutoff pressure, which could be considerably higher. And because we know we want steady speeds to our hydraulic cylinder, we don't wish to see any fluctuation in speed. Every time we take a brick off the stack, or every time we add a brick to the stack, the pump knows to adjust itself accordingly so that the flow rate through the needle valve doesn't change. That's the nature of a load sense system, and that's a brief introduction to load sense pumps. Thanks for watching.
We have hundreds of interactive resources like this live schematic, so you can try it.
Clear, pretty clear. So again, what happened then? is that, is using this measure here and is using that information to set how much the flow is produced to the system. And again, the idea, the magic thing is that, if here the pressure, well, it was using this PSI, we don't use that because we're here in Europe, so we wanted to use SI units, which we don't, because usually in hydraulics we say bars. It's not exactly rough, strictly speaking, SI units, but let's say that here is 100 bar. Right before this, you can call this is a direction valve. There is always a bit more pressure available, and how much more? That depends on that margin pressure that was explaining in that video. So this is, let's say, if the margin pressure is a 50 bar, then what is available here is a 150 bar. That's how it works. And now the beauty of the method is, or this procedure is that these measurements can come from a number of different locations in your hydraulic circuit, and then you just select the one that is having the lowest value. Okay, so having the one that is having the maximum value, that's how it goes. Mathematically, it goes such the way that this is that margin pressure, and then you have this goes in the right. You have the number of measures here from different locations from your hydraulic circuit, and then that's compared the pressure that is in right after the pump. And then again, this is time constant, and this is flow produced by your system. That's the idea. So a bit more clever way to make to do the pump control. And here again, you're measuring, in this case, you're measuring the pressures from 2 different locations, and then you're selecting the highest, and that's how you're setting your pump pressure. The magic K that is needed in the equation, that's the one you can get from manufacturer's catalog, from the characteristic curves that are provided, explaining the features of every single pump. This is, characteristic curve, and from that you can get that K. And, this is not even very significant, as, that values are typically very close to each other in different pump types. Now comes moment of truth. In hydraulic model, pump is assumed to produce pressure for hydraulic circuit, oil flow for hydraulic circuit, temperature for a hydraulic circuit, voltage to electric circuit. But which is correct? So okay, so let me put the sockative on. Okay, I have so what happens here? Is there, because it was a 69, I'm quite sure it was 69 answers. 99%, correct. But I was looking.
People to answer even though that you're looking at the situation,
And they come and answer incorrectly. That's what wonders me the most. How can I prevent this to happen? Next, so I should do the next. Okay, here. But then you will see the next question already. Okay, now we have 75 students. And now I'm asking, in a hydraulic model, pump is assumed to produce pressure, oil flow, temperature, voltage. Okay, now, here's the deal. What I just did during the break is that I added one more question. I added one more question that is related to my example, because for some reason I don't want to lose the hope. This is the hope what is keep on me running. So I still want to make a final attempt, even though that we are, if not scoring 100%, fine, because we have still a final attempt left. But that's then the final attempt. Okay? But what do you say about the success rate here today in this particular question? Because I don't think it is 100%. I don't think so. But how much? 90? Yeah, maybe you're right about that. It could be the case. I'm just personally not willing to say that in loud. So that's that will be good. That will be good. 80 would be quite low. You say 70, so 70 is super low. Okay, so you all done? Not yet? You guys all done? Okay, now the thing is that unlike participants here, there's always a certain delay. So, I need to give them some time to answer this question. But now we have 15 students that are still thinking. Yes, 15. Soon I will move on. So what I will do then is that I will get started with my example. And in this example, once I'm explaining a few matters related to this, and then I will go back and check out that in-class quiz. So here's the hydraulics circuit that I would like to model. And let me explain what I have here. So I have here a pressure source. Pressure source is then connected to direction valve, which is magnetically operating. This direction valve is having 3 operation positions and 4 ports that are connected. And then direction valve is then connected to throttle valve, and the throttle valve is then connected to piston side of the hydraulic cylinder. Now piston rod side is connected directly to direction valve, and here this is tank line. This is what I would like to model. So let's see how much is needed to make a model like this. Obviously, what I really wanted to do here is that I would like to learn how much force this hydraulic cylinder is capable to produce. And in order to know that, I have to know how much is a pressure here in a piston rod side and how much is a pressure here in a piston side. That's, in short, what I need to do. So, again, I am a big fan of these simple steps. Again, we're gonna follow the steps. And here, similar way, like in a multi-body system dynamics, you're following these steps and you will get all necessary equations automatically. Well, you will get it. Now, I'm not sure if it is automatically, but you're gonna get it. First step, which is obviously the most important step to take, is that we have to make an ideal picture about what are the pressures and how are the positive flow rate directions. We concluded earlier that in a system like this, I can assume that the pressure in a hose or the pipe that is connected from the direction valve, the throttle valve, I can assume that pressure to be equally distributed. So here's the first volume. The direction is
downwards. Both of them are down.
which one?
In the
This one?
not there, but direction control valve.
This one?
No, after that, yes, it's going there, going back, but if it's the opposite side, then it's
Oh, okay. So let me explain what I have here. So maybe this was a bit unclear. So I'm just setting that the flow, what I'm first of all doing is that I'm discretizing my hydraulic circuit to volumes where I'm assuming pressure to be quite distributed. So that's kind of the first step to take. That's kind of sub-step within the step number 1. So I'm going to make an assumption that the pressure here is equally distributed and the pressure here is equally distributed, same as here. So I have 4 different locations where I'm computing the pressure. Now what I'm doing is that I'm setting my flow rate to having positive direction, and they can be whatever you want. There is no rule how to set this. Only thing that is important is that once you make your decision, you must be consistent. You cannot change your direction any longer. That's what you want, right?
yeah.
Okay, so No, I'm just, just making the rules to myself, nothing else. The first rule is, the whatever flow is coming off from the direction valve is assuming to have this positive direction. And whatever, flow is going this direction is positive through this throttle valve. And then whatever is going towards direction valve is having the positive value. That's just the rules that I set. If you're not comfortable with these rules, go ahead and reset it, but be consistent. Okay? Now comes, how is that I can compute this differential equations that then the step number 2 is not that differential equation, but forming the equation describing the volumes. The first volume is not variable volume, it's just the hose volume, nothing else. Second one is a variable volume because the piston can go up and down and it's measured by x. X multiplied by corresponding cross-section area gives me the volume associated to this part that is then added with the hose line that is connected to cylinder. Then I have here again the volume that is associated to the piston rod side plus the hose that is connecting that to direction valve. That's my volume number 3. And now the next step is that I can compare the effective bulk modulus. I'm using the equation that I already practiced to use a couple of weeks back. So I'm comparing the bulk modulus for my first volume, second volume, and the third volume. I'm skipping the details because the next one is then what really matters. Now, depending on the rules that I set to myself, I'm able to create the differential equation. Let's look at the examples. I have flow rate here that is coming to volume that is having the ID number 2. Now, the flow rate is having the positive direction because it's producing more flow rate than this volume that I'm looking at. Now, if X is having positive direction, this direction, when the piston is moving upwards, I'm losing flow rate because it's kind of sucking the more flow to system. So that's why the piston motion is having here a minus sign. You with me?
Yes.
Then P, when this is, piston is moving this direction, is pushing more flow to this particular volume. That's why this is having the positive sign, and then this is taking flow off, so that's why this is having a negative sign. Clear? What is missing is this one. How is it you can model the pressure associated to volume number 1? Well, it's going to be, again, let me show it to you, because it goes such the way that, this volume, this is coming in, this is leaving out. Okay, can you do it? You can do it? By the way, I don't know, have you watched that YouTube about the worst professor ever? Have you seen it? Yeah, it's all about, can you do it? Just keep on repeating that. So I kind of trying to avoid that, so to make sure that I'm not end up to be in that channel. But, now let's take a look. So what I'm gonna do next is that I'm gonna close this. Candies or not? No candies. No candies. You don't even believe by yourself. Come on. Where's your can-do attitude? Okay? Okay, so not bad, not as high that I thought, but it's still all right. The pressure is a source of flow rate, so it's like
It's like 100.
what is that?
It's like 100.
Yeah,
You can assume because no other answers.
yeah. Well, yeah, that's right. That's right. No one is saying temperature, which is very good news, and no one is saying voltage, which will be a big surprise if there is someone saying voltage. No discussion whatsoever related to voltage. But now, here is when the final chance comes into play. This is it. So this is my last in-class quiz in this course, and it's this one. pressure and the volume ID1. So it's this one. So let me emphasize this one here. And that can be computed, but again, you know, I need to apologize that the P dot, this of course should be P dot. And I guess that the dot is there, but it's just a very weak. So how is that you can compute it? Which one out of the 4 options is the correct one? Which is taking this flow in and this flow out? Only one is correct. So these are the choices. So this says that this is, well, you can see the notation. Let me just make this clear for you. Hold on, here. Okay, is it big enough? How can I make this bigger? No, I know how can I make it bigger. Okay. Oh, but now you don't see the options. Okay, look at this and put these in your mind. You know, what are the positive directions, and then okay, there it is. Okay, I think that is clear enough. Okay, now next. So the last one. Maybe this is too difficult. Is it? What do you say? Kind of like so. Now the thing is that I cannot move from this slide because as soon as I move on in my example, I will release the correct answer. And that's like serious cheating in my mind. So I'm not going to do that. But which one out of these 4 options is the correct one? Which is taking flow in correct way and taking the flow out in a correct way. So it's all about the plus and my signs. Plus and minus signs. Okay, so let me go. Would you like to see this more, or are you good? It's clear. So it's clear. Okay, so let me take a look. I will leave it as it is, and then I will look this one. So I have 31, 34, 5 students that are entered the answer already, but I need more. Forty students. Last time I think it was 60. What was the final number last time? I think it was 67, right? Okay. So I will give you another, say, 15 seconds. And then I'm done. Okay. It was that 15 seconds. Still more is coming in. You all done? Okay, what's the correct one?
I was confused between A and C.
I got it. So you were with this and this. You know, here this is positive, meaning that it's producing more flow rate.
Yeah.
So the arrow is towards the volume. So it's have to be positive. This is taking off it, so that's this one. Okay. So now let me here. Can I close this? Okay, so now based on that discussion, I don't think it is 100%. Is it? 90. So
Still 11% at C.
still it's you know. Okay, but not that bad. Okay, but now it's changing again. So how can I close this? So what should I do? Finish. Okay, so no, I don't want to show this to you. Okay. Anyway, so we'll get back to that a little later today. Now let me close to this example. And how is that this first one is a correct option? Because the flow here is coming in. So if it is coming towards the volume, it is positive. And if it is leaving from the volume, like this is leaving, then it is minus inside. So that's the difference. Okay, so let me just close this example because there is something else that I would like to discuss with you. So that's the correct one. So that's step number 4, create the differential equations. Okay, step number 5, modeling the valves and flow rates. Now, depending on the spool position, you can have 3 different scenarios, like it is shown here. This is exactly what we discussed earlier in a case of direction valve. And in the case of throttle valve, the flow rate is modeled by using this simple equation, algebraic equation. And then final thing is force produced by cylinder. That's the one that you're solving the pressures and you're substituting the values that is part of the equation, and you have some kind of estimation about the friction. Now look at the friction is assumed to be linearly related to velocity, not according to that polynomial expansion, but more a simple expression. Okay, but the damping some kind, friction some kind helps to damp if there is a vibration in the system. Okay, now next 15 minutes or even less than that, shortly about flexible bodies. This is a newsflash for you. And something that we will get back in the laboratory course, but now I would like to shortly explain, what is the ways that you can model deformable bodies. I'm not going to explain in details this method, but I'm shortly noted that there's a simple method called land mass approach, which actually is not within the category of flexible multi-body dynamics, but it's just a collection of rigid bodies that are connected together in a special way. Then there is a possibility to use combination of finite element method and multi-body system dynamics. That's what is used in industry in today's examples or today's problems, to solve today's problems. So it simply means that you take your finite element model and you combine that together with the multi-body dynamics, so then you can describe deformable bodies very accurately. And then there are some very unique methods that are designed to account very large deformations. And now, why is that I'm explaining this to you? Well, this is simply because there was a few years back, there was a hope, and this hope was actually provided by students. And according to this hope, they say that, a professor should explain more about the research we're doing here in the university. That's what I'm going to do here. So what we're doing mainly, many of the studies we're doing in my team are related to flexible multi-body dynamics. And we're developing the formulations to describe deformable bodies, and we're particularly focusing on large deformation cases. Those are the cases where there is a very significant amount of deformation, which is needed in, for example, in a cloth modeling, in a soft tissue modeling in a human body, and many other applications. And then, in addition to that, we're doing this real-time simulation that I'm going to explain to you next Tuesday. Okay, but this is a little bit of explanation how is a flexible bodies. Well, I'm sure this is not surprising you when I'm saying that there is no such thing like rigid bodies. Every single body is a deformable body, flexible body, but the question is when the deformation is significant enough that it affects the dynamic performance. That's very hard to say, and there is no general rule to make that decision, but depends on your common knowledge or engineering knowledge. But of course, reason to introduce flexibility to your model is to make more accurate, more physics-based models. And you can do that in a number of different ways, like I explained in a previous slide. But now this family or this method associated to flexible bodies, those can be categorized to 2 different fields. There are they can be, first of all, categorized to method, where the deformation is assumed to be small, and then on the other hand, the family, where the deformation is assumed to be large. So it's all about how the strain displacement relationship is assumed to be. And this is what I'm expecting that you learned already from the strength of materials course. And explaining you what exactly I mean about this large deformation and small deformation. I have here an example, which is a cantilever beam. And what I'm doing for that cantilever beam is that I'm loading the free end of the cantilever beam. Okay? So what will happen because of this force is that there is a certain amount of displacement. There is a deformation that is measured in terms of displacement. Now say that in the end of this cantilever beam there is a displacement u that is having some numerical values. Now how is that I'm relating this displacement to strain? That's something that is very important. Often when the deformation is small, I can assume that relation to be linear. All right? But the consequence, if I make this assumption that the this strain displacement relationship is linear, what happens is that when I do that assumption, then what happens is that the free end of the cantilever beam will remain on this loading line. But that's fine if the deformation is small, like shown in this picture. But as soon as the deformation becomes large, it's no longer realistic, because if I'm having a lot of force, the deformation will look like something like this. You don't find that in real life, because in real life the deformation would be something like this. What's the difference here is that there is a certain amount of deformation in axial direction. And that you can only capture by having nonlinear strain displacement relationship. This is something that when you look at the literature is called geometrical nonlinearity. That's what it is called. Now the studies we're doing in my team, we are assuming that relation to be, of course, nonlinear. Then we can capture that large deformation. Then there is also this material nonlinearity, because strain is associated to stresses. Let me make it a better drawing. Stresses. How is this relation? That there is this famous curves that shows how the steel materials are behaving. So such the way that this is a strain and this is a stress. That they are typically linear until they reach the certain point. And after this certain point, they becoming nonlinear when the plastic deformation takes place. And if that plastic deformation takes place, once you take the loading off, the system are not becoming back to original configuration, but is having some certain amount of plastic deformation. This is typically not accounted in a multi-body dynamics, because even though that in a cranes there could be very large deformation, there is almost no case with the plastic deformation, because the plastic deformation, if that happens in a real life, it is very, very bad design. Think about the crane that you left something when the first time, and it will be left bended configuration. No good. Not very good. Okay. So here's an example. Here is a cantilever beam with and without nonlinearity. So what I have in a cantilever beam is a pendulum structure, and in a case that is closer to you, I'm accounting that nonlinear strain displacement relationship. In the clay case closer to wall, that is not accounted. Okay. Now, why this is then important? It's important because, in a trend is that in a multi-body system dynamics, everything started in a rigid applications, where we assume bodies to be having no deformation no matter how much force is imposed to your system. Then soon it becomes clear that if you wanted to have more accurate models, you must be able to describe deformable bodies. And then there was an introduction of methods that were able to account small deformation, which is typically fine when you're looking like connection rod or simple structures, cranes and such. And then soon people realize that there is even more complicated components, like for example belts, biomechanical applications and so on and so forth, where this small deformation is not enough. And this is where the research is at the moment. So this is still more or less under development. There's already some methods available out there, but they're suffering from numerical inefficiencies. So it's still something that more work is needed. So that's a little bit of for your information. And now, 4 minutes, which I will shortly spend you to explain the first method. That is very simple method to describe the flexibility. And rest I will leave for next Tuesday. I'm not going to spend too much time next Tuesday about flexible bodies because there is so much stuff that is related to real-time simulation. But in the first way to describe flexible bodies is that you can simply take your original, typically beam-like body, and you can replace that by a number of rigid bodies. So one body will be replaced by a number of bodies. And what you're going to do in addition to that is that you will introduce the spring elements between these bodies. And these spring elements will be constructed such the way that there is a stiffness for all 6 degrees of freedom in a spatial case and 3 degrees of freedom in a planar case. And that makes it possible to have, some kind of simple description of deformable bodies, because altogether these rigid bodies plus stiffness elements, they behave like deformable bodies. Now, this is a very pleasant approach because here this follows the exactly same theory than in a rigid multi-body dynamics. No difference whatsoever. You just keep on adding the number of bodies, a number of externally applied forces, and that's it. Very pleasant. It can be applied to, typically the beam-like structures, and it can even account this geometrical nonlinearity that I explained in a few slides back. And it is a quite all right method, but it is computationally very, very slow. Why is that? That I will explain you just before we closing for today. Here are the few examples. It's still being used in some cases like modeling cables. Like here is a crane, tower crane, a little bit of small figure, but there is a cable that is going down here, so there will be a better view for that. And that's modeled by using this simple lamp mass approach. This is a cable or wire rope that I'm referring to. And this is, by the way, having this string effect too. Once the wire rope is without loading, the frequency is low. And as soon as you're loading it, the frequency is becoming higher. You can clearly see that when you look at that particular detail. And in the past, it was used in other application than in the cables, like in the cranes, like this one here. This was modeled flexibly by using this lamp mass approach. And just to conclude this is computationally expensive because this usually leads to cases when system becomes numerically stiff. Numerically stiff is something that you have high frequencies and low frequencies in your model altogether, simultaneously. And this is typically something that the integrators are having a hard time to deal with that. And typically they're setting their time step such that, these high frequencies are accounted. And often they have no particular meaning, but still they slows down the computation. But we can get back to that in this laboratory course, and it is mainly can be used in a beam-like structures. Material damping is quite simple, but very easy to use, simple theory. Okay, with that, I'm gonna close because it's 4 o'clock, and next Tuesday it will be final things about flexible bodies, and then real-time simulation, and then we're done. See you on Tuesday. Okay, thank you.